How the redshift of gravitons explains dark matter and dark energy. Furman J. Oliveira. Affiliation: East Asian Observatory / James Clerk Maxwell Submillimeter Telescope. December 20, 2022. Abstract. The theory that gravitons lose energy by way of gravitational redshift while traveling in a gravitational field is applied to the expansion of the universe and to spiral and dwarf galaxy rotation curves using Newtonian physics and general relativity. This is a graviton self-interaction model which derives an expansion equation which is identical in form to the standard lambda cold dark matter model. In the domain of galaxies, spiral and dwarf galaxy rotation curves are matched using only baryonic mass. Thus, the requirement for dark matter and dark energy in the universe is replaced by this paradigm. Keywords: gravitons, gravitational redshift, baryon mass density, supernovae, spiral galaxies. Prelude. This is an audio-oriented version of the paper, How the Redshift of Gravitons Explains Dark Matter and Dark Energy, by Furman J. Oliveira, Journal of Modern Physics, 13/11, November 2022. DOI 10.4236/JMP.2022.13111084, which is open access. No major changes were made, except to improve the audio rendering by placements of spaces in equations and plus signs to some exponentials, etc. The artificial intelligence reader performs well for text but falls short for mathematics. We apologize for any inconvenience this may cause. Introduction. This paper describes a theory of gravitons acting in the universe, and it supersedes the theory expressed in reference 1. In regards to the expansion of the universe. We will also describe the action of gravitons in galaxies reference 2. Assuming that gravitons are the agents of interaction in a gravitational field, then our goal is to describe how the gravitational redshift of gravitons shows up as what has traditionally been labeled as dark matter and dark energy. We will show how the redshift of gravitons can explain both of these phenomena using high-precision data. Throughout this paper, all reference to sources of mass and test particles are assumed to be of baryonic nature, unless otherwise specified. When we speak of the graviton mass mg, it is a relativistic mass. We assume gravitons are bosonic particles which travel at constant speed c in vacuum, where c equals the speed of light. Gravitons traveling in a gravitational field between a source mass m and a test mass m, modeled by the equivalence principle as an accelerating system, should experience an average energy loss of delta xi. Due to motion in that field, over a short time period delta t equals delta r/c, where the acceleration at a point r in the field is given by a equals minus gm/r2. The energy loss is expressed differentially as delta xi equals minus mgc2, delta vc equals minus mgc, a delta t equals minus gm mg r2 delta r, 1. Where mg equals m/n is the average relativistic graviton mass, n is the number of gravitons, m is the test mass, delta v is the change in the free fall velocity of the system observed from an inertial reference frame, g is Newton's gravitational constant, m is the baryonic mass of the field source, r is the distance between the center of the source and the location of the moving gravitons. Delta t is the short travel time of the gravitons at speed c over distance delta r. The energy change is a loss, negative, because the velocity change delta v is in the same direction as the motion of the gravitons, so that for an inertial observer moving in the same direction as the graviton, the energy of the graviton is redshifted. We call this effect of energy loss a gravitational redshift which, as we have described it, resembles a Doppler effect. Since gravitons are agents of the gravitational field, our model is essentially an attempt to describe the graviton-graviton interaction as in the self-interaction of a quantum gravity theory reference. 3. Gravitons exist and travel in a gravitational field, which in principle is equivalent to an accelerating system. Assume that the total graviton energy for a system of two masses is expressed by psi equals gmm r2, where m equals nmg is the total graviton mass associated with the test. Mass m, where mg is the average graviton mass and n is the number of gravitons. The total graviton energy decreased delta xi due to its freefall in the gravitational field of mass m, when viewed from an inertial system, is expressed by delta xi equals minus psi delta vc equals minus gmm. R delta vc equals minus gmm. Rgm. C2 R2 delta R3. Where, as in equation 1, delta v equals gm/c r2, delta r is the velocity increase in the accelerated reference frame equivalent, according to the principle of equivalence, to the gravitational field of mass m at the position r. Gravitons in an expanding universe. Consider the universe as a sphere of interior baryonic mass m with a thin spherical shell of mass m. The masses m and m are constants. The thin shell has a radius r, t, at time t. Only the mass interior to the shell has an effect on the shell. The total graviton energy psi, t, within the shell at time t is given by equation 2, where r equals r, t. Assuming isotropic uniformity, the mass density ρ, t, within the shell at time t is ρ, r, t, equals 3m4 pi r3, t. 4. At the present epoch of time t0 the baryon mass density is ρb, which is given by ρb equals 3m4 pi a3, 5. Where a equals r, t0, is the radius of the universe at the present epoch. Energy loss due to gravitational redshift. Since the potential function phi, r, equals gmm/r is defined as having zero energy at infinity and having a negative energy at position r, likewise we define the graviton energy loss to be zero at infinity and negative at position r, applying equation 1 to the n gravitons in free fall in the expanding universe we have the energy loss. Increment xi dm equals k dm z increment psi 0 and delta xi equals minus k dm z r. Infinity minus gmm. R2 dr equals minus k dm gmm. R6, where kdm is a coupling constant to be determined by observation and the extra minus sign accounts for an energy loss because the gravitons travel in the same direction as the free fall velocity change and appear redshifted to an inertial observer also moving in the same direction. Substituting for m from equation 5 and simplifying yields, increment xi dm equals minus kdm 4 ga 3. 3m rho br. 7. This energy loss component is the so-called dark matter. Energy loss due to expansion. Gravitons traveling at speed c in the vacuum of the expanding universe undergo cosmological redshift in 3 dimensions on the way to interaction with the masses. We express this redshift by applying the 3D velocity differential, delta Vx delta Vy delta Vz /c3, to the total graviton energy psi from equation 2, and applying equation 3, in the 3 spatial dimensions, given in the form delta xi equals minus gmm. R delta Vx delta Vy delta Vz c3, 8. Where the negative sign is applied because the motion of the gravitons is in the same direction as the freefall in the field. We can convert the 3D velocity differential to a ratio of 3D volume differential by the construction delta Vx delta Vy delta Vz c3 equals delta x c delta tx delta y c delta ty delta z c delta tz equals delta x delta y delta z c3 delta tx delta ty delta tz. 9. Where x, y, and z are Cartesian coordinates, Tx, Ti and Tz are independent times and where delta Vx equals delta x slash delta Tx, delta Vy equals delta y slash delta Ty and delta Vz equals delta z slash delta Tz. Furthermore, we convert the volume differential in Cartesian coordinates to radial coordinates, in the form delta x delta y delta z equals 4 pi r2 delta r. 10. Now, applying the transformations equation 9 and equation 10 to equation 8, while also moving the volume differential. C3 delta Tx delta Ty delta Tz to the left-hand side of the equation we get delta xi, C3 delta Tx delta Ty delta Tz equals minus GMM R 4 pi r2 delta r. 11. The left-hand side of equation 11 is a quadruple differential whilst the right-hand side is a single differential. Integrating both sides of equation 11 yields a 3D increment d equals z t0 z t0 z t0 z increment psi 0 delta xi, c3 delta tx delta ty delta tz equals z r 0 minus m g m r 4 pi r2 delta r equals z r 0 minus 4 pi m g m r delta r equals minus 8 pi 2 g 3 a 3 m rho b r2. 12. Where the expansion time is taken to be t equals a slash c. 13. Where a is the present radius of the universe and d is a dimensionless coupling constant and where, in the final line we substituted for m from equation 5. Rearranging equation 12, we get the graviton energy loss due to the expansion of the universe, the so-called dark energy component. Increment d equals minus d8 pi 2 g 3 m rho br2. 14. We will subsequently show that the graviton energy losses increment xi dm and increment d can account for the expansion rate of the universe without dark matter or dark energy, which are required by the lambda cold dark matter cosmological model reference. 4. The total energy of the shell of mass m, where mm, having kinetic energy, gravitational potential energy and energy loss due to the cosmological redshift of gravitons equation, 14, is expressed by 12 mv2 minus gmm r plus increment xi dm plus increment d equals 12 mv2 minus 4 ga 3 m rho b r minus kdm 4 ga 3 m rho b r minus d8 pi 2 g 3 m rho br2 equals minus 12 mc2 ka2. 15. Where the term on the far right is the total energy, where k is a constant, curvature, with dimensionality, length, minus 2, a is the present radius of the universe and m is the mass of the universe. Multiplying equation 15 by 2/mr2 and simplifying, we get the expression for the expansion of the shell. V2 R2 equals 8 ga 3 rho b31 R3 plus kdm 8 ga 3 rho b31 R3 plus d16 pi 2 g rho b3 a3 minus kc2 a2 R2. 16. Note that the shell mass m can be made arbitrarily small compared to the universe mass m. Define the distance r by r equals a. 17. Where the time-varying scale factor a is dimensionless with 0 a less than or equal to 1. Using equation 17, the velocity v takes the form v equals dar dt equals a did dt. 18. Substituting equation 18 into equation 16 gives us 1 a did dt 2 equals 8 pi g 1 plus kdm rho b3 a 3 plus 16 pi 2 deb 3 minus kc2. A 2. 19. Putting equation 19 in terms of the mass densities we have. 1 a d dt 2 equals 8 pi g 3 rho m a plus rho dm a plus d a plus rho k a 20. Where rho m a equals 1 plus k dm rho b a 3 21. Is the mass density composed of baryons and graviton energy loss mass due to gravitational redshift, an apparent dark matter mass density, d a equals 2 deb 22, is the graviton energy loss due to the expanding universe, an apparent dark energy mass density, and rho k a equals minus 3 kc 2 8 ga 2 23 is the curvature mass density. Define the Hubble parameter h, t, by h, t, equals 1 r dr dt, 24. Where, by equation 17, r equals a, equation 24, can also be written as v equals dr dt equals h, t, r, t, 25. Which is the Hubble law for h0 equals h, t0, where t0 is the present epoch of cosmic time. Thus, h, t, defined by equation 24, is the general form of Hubble's law reference 5. Substituting h, t, for d slash a dt in equation 20, with some manipulation, we get rho c, t, equals 3h2, t, 8. Pi g equals rho m, t, plus d, t, plus rho k, t, 26. Where rho c, t, is called the critical mass density at time t, dividing equation 26 by rho c, t, yields the parametric equation. Rho c, t. Rho c, t, equals c equals 1 equals m, t, plus d, t, plus k, t, 27. Where m, t, equals rho m, t, slash rho c, t, d, t, equals d, t, slash rho c, t, and k, t, equals rho k, t, slash rho c, t. At the present epoch t0, the mass density parameter is m, t0, equals 1 plus k dm, b, 28. Where b is the baryon mass density parameter, the graviton expansion energy loss mass density parameter is d, t0, equals 2 deb, 29. And the curvature density parameter is k, t0, equals minus k, c2. h20. 30. General relativity for an expanding universe with graviton. Interaction. The Friedmann-Lima-Robertson-Walker, FLRW, metric line element references 6, 7, 8, and 9, in terms of the scale factor. A, t, is ds2 equals minus c2 dt2 plus a 2, t, dr2. 1 minus k r2 plus r2 d2 theta plus r2 sin 2, theta, d2 phi, 31. Where the scale factor 0, a, t, less than or equal to 1 and the curvature k has units of length, minus 2 where k is 0, k is 0 or k equals 0. The Einstein equations reference 10, reference 11, in trace reverse form is r nu equals kappa t nu minus 1 2 tg nu, 32. Where r nu is the Ricci tensor, T nu is the energy momentum tensor, T is the contracted energy momentum tensor, G nu is the metric tensor defined by equation 31, and kappa equals 8 pi g slash c4. Define the energy momentum tensor T nu of a perfect fluid. T nu equals rho c20000 p0000 p0000 p. 33. where, referring to equations 21 to 23, for the mass densities, the total mass density ρ is given by ρ equals ρm plus d plus ρk, 34. Where ρm equals 1 plus kdm, ba 3 r 3, 35. D equals 2 deb, 36. ρk equals minus 3 ka 2c 2 8 pi gr2, 37. And where the current baryon mass density is ρb equals ρcb, 38. Where B is the baryon mass density parameter. We have assumed the equation of state for the relativistic particles PdE equals dc2, with D equals minus 1. We are neglecting the radiation density, photons and neutrinos, and we will justify this when we fit the model to ESNA IA data. Solving the Einstein equations equation, 32, given the mass-energy tensor equation, 33, and simplifying the results, yields the equation for the rate of change of the scale factor. A 2 equals 8 pi g3 rho minus ka2. 39. Assuming k equals 0 for no curvature, and the total mass density given by equations, 34, 38, the Hubble parameter h, a, is h, a, equals h0 r, 1 plus kdm, b a 3 plus 2 deb, 40. Where b equals 8 pi g b slash 3h20. Fits to type Ia supernova data and comparison with the standard model. The scale factor A has the relation to the cosmological redshift z expressed by A equals 1 plus c. 41. An increment of comoving distance delta dc defined in terms of the scale factor is delta dc equals c dt A equals c da a 2h, a, 42. Where we use the definition equation, 24, of the Hubble parameter. In terms of the cosmological redshift z, the comoving distance is delta dc equals c dz h, z, 43. Where we use the fact that d equals minus dz slash 1 plus z, 2 equals minus a 2 dz to transform equation, 42, dropping the minus sign. The flux phi 0 from a distant light source at redshift z is defined in terms of the observed luminosity Lo equals L slash 1 plus z, 2, where L is the luminosity of the emitting source. Phi 0 equals L 4 pi, 1 plus z, 2d2p, 44. Where dp is the proper distance. The luminosity distance, from equation, 44, is 1 plus z, dp equals r L 4 pi phi 0. 45. The luminosity distance, from equation, 43, is dl, z, equals 1 plus z, dc equals 1 plus c, zz. 0. C dz h, z, 46. Where dc is the comoving distance and where h, z, equals h0 q, 1 plus kdm, b, 1 plus c, 3 plus 2 deb, 47. And we change the negative sign to positive by inverting the limits of integration. The form equation, 47, of the Hubble parameter h, z, is identical to that of the standard model. Therefore, fitting to the ESNA IA data will be identical. The magnitude is defined in the standard way. Mu, z, equals 5 log, dl, z, minus b plus AF, 48. Where b is the source magnitude and AF is an offset. Generally, the source magnitude is combined into AF. We applied equation, 48, in a fit to 580 type Ia supernovae, ESNA IA, magnitude data from the Supernova Cosmology Project Union 2.1 data set reference, 12. With Hubble constant h0 equals 70 km s-1 mpc-1, densities m equals 0.271, d equals 0.729 reference, 12, and offset AF equals -87.441, the fit to the SNA-IA data set obtained a two-parameter chi2 is equal to 0.9769. Figure 1 shows the fit to the data. Regarding neglecting the radiation density in our model, the radiation density parameter of photons, with h equals 0.7 is given by reference, 13, r equals 2.47 times 10⁻⁵, slash h2 is equal to 5.04 times 10⁻⁵. At the maximum redshift of Smax equals 1.5 for the SNA-IA data, the relative magnitude of the error rad in comparing the radiation and matter densities is rad equals r, 1 plus Smax, 4. M, 1 plus Smax, 3 equals 4.6 times 10⁻⁴, 49. Which justifies ignoring the radiation density in the fitting. Assuming that the curvature k equals 0, so that k equals 0, then from equation 27, we have for the present epoch 1 equals 1 plus kdm, b plus 2 deb, 50. And from equation 29, d equals d2 pi b, 51. For example, for d equals 0.721 and b equals 0.049, which is in the Big Bang nucleosynthesis, BBN, allowable range reference, 14, we get a value of the coupling constant d equals 2.342. Also, from equation 28, we get kdm equals m slash b minus 1 is equal to 4.694. The expansion time from equation 13 has the value t equals 1 slash h0 equals 13.97 times 10 plus 9 year. Figure 1. Supernova Cosmology Project Union 2.1 SNA-IA magnitude versus Redshift data points with error bars. The solid line is the fit for the Graviton model with m equals 0.271 and d equals 0.729 with a two-parameter. Chi2 is equal to 0.9769. The dotted line is the fit for the LCDM model with the same parameters and the same Chi2, the Graviton model and the LCDM model fits are, obviously, identical. Gravitons in galaxies. Integrating equation 1, up to radial distance we obtain the average energy change per graviton increment xg expressed by increment xg equals minus cr 0 mgc2 do c equals minus cr 0 milligrams gm r2 dr 52. Equation 52 describes the gravitational redshift of the energy of the average graviton as it travels from a lower, more negative potential to a position r of higher, less negative potential and is consistent with energy conservation. Now, consider the energy for a galaxy of mass m interior of a small mass m in a circular orbit of radius r. The gravitons traversing the distance at light speed from the interior mass to the orbiting mass will experience a decrease in energy as described by equation 52. Increment psi equals n increment psi g, where n is the number of gravitons. Taking the energy loss of the gravitons into account, the total orbital energy of the orbiting mass m is 12 mv2 minus gmm r plus kg n increment psi g equals e, 53. Where v is the rotational velocity of the orbiting mass, kg is a coupling coefficient, a constant for each galaxy, and the total energy E equals minus gm slash 2r. Using equation 53, by expanding increment psi g using equation 52, with m equals n mg, multiplying by 2 slash m and moving all terms except v2 to the right-hand side, we obtain the expression for the orbital velocity. V2 equals gm, r. r plus 2 kg z r. 0. gm, r. r2 dr. 54. As an approximation, we model the mass distribution of a spiral galaxy by a spherically symmetric distribution ρ, r, even though a mass density distribution consisting of a spherically symmetric central bulge surrounded by an axially symmetric thin disk would be more realistic. Then the mass m, r, of the galaxy within the radial distance r from the galaxy center is given by m, r equals z r. 0. 4 pi rho, r, r2 dr. 55. Coupling coefficient kg. Under our assumption that the coupling coefficient is constant for each galaxy, equation 54 can be solved for kg at the galaxy edge, where r equals rf and v equals vf, giving kg equals v2f minus gm, rf rf. 2r rf 0, gm, r, r2, dr. 56. Where m, rf equals mb is the total baryonic mass in the galaxy. By Newton's gravitational law, at the galaxy edge, the final velocity vf is related to the total apparent mass mn contained within the radial distance rf by v2f equals gmn rf equals g mb plus md. rf, 57. Where mn equals mb plus md, where md is the total apparent mass due to the graviton energy loss, the mass of the so-called dark matter. The total apparent dark matter in a galaxy is given at the galaxy edge by md obs equals v2f rfg minus mb, 58. Using the results from analyzing galaxy rotational data, we can estimate the dark matter by equation 58 as md, and substituting that and equation 57 into equation 56, we arrive at a formula for estimating kg as kg equals md obs 2 rf r rf 0 m r r2 dr. 59. The Einstein equations for galaxies with gravitons. Assuming a spherically symmetric mass distribution for a galaxy, we will use the Schwarzschild metric to describe the motions within the galaxy. The Einstein equations for the region outside of a spherical mass distribution is r nu equals 0, 60. Where r nu is the Ricci tensor. The metric element we use is defined in spherical coordinates. ds2 equals minus e nu c2 dt2 plus e lambda dr2 plus r2 d theta 2 plus sin theta d phi 2. 61. Where e nu equals 1 minus 2 gm, r. c2 r, 62. E lambda equals 1 minus 2 gm, r. c2 r minus 1, 63. And where m, r, is the mass within radius r. From the metric element equation, 61, the metric tensor is g nu equals minus e nu 0000 e lambda 0000 r2 0000 r2 sin 2 theta. 64. Since the metric equation 64 does not depend on time t and angles theta and phi, it follows from Hamilton's principle and the Lagrange equations 1 that d d tau e nu dt d tau equals 0, 65. Implying that the total energy E is E nu dt d tau equals EMC2, 66. From which we get E nu C2 dt 2 d tau 2 equals E minus nu E2 M2 C2. 67. And similarly for the phi component, we have that d tau r2 sin 2, theta, d phi d tau equals 0, 68. Implying that the specific angular momentum is r2 sin 2, theta, d phi d tau equals h, 69. From which we get r2 sin 2, theta, d phi 2 d tau 2 equals h2 r2. 70. For motion in the plane defined by r and phi, d theta slash d tau equals 0, where theta is defined as theta equals pi 2. 71. 1 Wikipedia, Schwarzschild geodesics, https://en.wikipedia.org/Schwarzschild geodesics. Equation of motion. We derive the equation of motion using the metric element equation, 61, where ds2 equals minus c2 d tau 2, where d tau is the differential of proper time tau. Dividing the metric element by d tau 2 and substituting from equations, 66, 71, with the metric element we get, dropping the theta term since d theta equals 0, ds2 d tau 2 equals minus c2 equals minus e minus nu e 2 m2 c2 plus e lambda dr2 d tau 2 plus h2 r2, 72. Multiplying equation, 72, by e minus lambda and simplifying yields dr2 d tau 2 equals e minus nu plus lambda e2 m2 c2 minus e minus lambda c2 plus h2 r2. 73. Substituting for e minus lambda from equation, 63, into equation, 73, and, since e lambda equals e minus nu from equations, 62, and 63, so that e minus nu plus lambda equals e0 is equal to 1, we get after simplification, dr2 d tau 2 equals e2 m2 c2 minus c2 plus 2 gm, r minus h2 r2 plus 2 gm, r, h2 c2 r3. 74. We assume that the mass m, r, within distance r from the galaxy center is given by the sum of the baryonic mass mb, r, within r and the mass mg, r, equivalent to the graviton gravitational redshift energy loss mass within r. The mass density of the baryons is given ρb, r. The total mass within r, which is the sum of baryonic mass and gravitonic energy loss mass, is expressed by m, r equals mb, r, plus mg, r, 75. Where the baryonic mass is mb, r equals zr. 0 4 pi s2 rho b, s, ds, 76. Where rho b is the baryonic mass density, and from equation, 54, we express the gravitonic energy loss mass in terms of the baryonic mass density by mg, r equals 2 kg r zr. 0. mbs. S2ds, 77. Where kg is a constant coupling coefficient which is peculiar to each galaxy. For circular motion, the specific angular momentum term in equation, 74, is h2r2 equals gm, r, r. 78. Dropping the constant terms in equation, 74, and substituting with equation, 78, the velocity of a particle in orbit in the galaxy is expressed by v2 equals dr2 d tau 2 equals gm, r, r plus 2c 2 gm, r, c2 r2. 79. Results for spark galaxies. We use the velocities from the Spitzer photometry and accurate rotation curves, SPARC, database reference, 15, and reference, 16, derived from near-infrared, NIR, surface photometry at 3.6 m. We select the spiral galaxies NGC 2403, NGC 2841 and dwarf galaxies DDO 154 and NGC 2915. From the photometric data, which has been reduced to the equivalent velocities for the galaxy bulge, disk, and gas mass content, we approximate the baryonic mass as due to a spherically symmetric distribution, which is given by the Newtonian relation for the velocity to mass contained within the radius r from the galaxy center, expressed by mb r equals r g of gas, r of gas, r, plus upsilon dsk, r, vdsk, r, vdsk, r, plus bull, r, of bull, r, of bull, r. 80. Where r equals re, I equals 1, 2, n greater than 1, and the number of radial distances observed, and the absolute values of the velocities are needed because they can sometimes be negative. Ref. 16, page 5. The velocities for the disk and gas from the table 2 of reference 15 are taken with upsilon asterisk operator equals 1. In our table 2, upsilon dsk and bull are the m/l used in equation 80 to make the fits. Using the spark results for the mass at r in terms of the gas, disk, and bulge velocities, where the mass internal to r is given by mb r of equation 80, the equivalent graviton energy loss mass is mg r equals 2 kg r sigma nj equals 1 z rj plus j less than 2 rj minus j greater than 1 mbs s2ds. 81. The predicted velocity equation, 79, is expressed in the form v2 rn equals g mb rn plus mg rn. Rn plus 2c 2g mb rn plus mg rn c2 rn 2. 82. Where n equals 1, 2, n greater than 1. We strive to obtain good fits to the velocity VOBs, rk, at each radial distance rk by minimizing the mean absolute error MAE between v, rk, and VOBs, rk, while iterating upsilon dsk, rk, for the disk and, when available, bull, rk, for the bulge. We constrain the mass to agree with the baryonic Tully-Fisher relation, BTFR, reference, 17, and reference, 18, mass for each galaxy. Table 1 lists for each galaxy the baryonic mass MB determined by the velocity profiles used in equation 80, the BTFR estimated galaxy mass, the mean data rotation velocity error var, the mean absolute fitted error MAE and the coefficient kg. Table 2 lists the average values for disk upsilon dsk and bulge bull mass to light ratios which were used in making each galaxy fit. Also listed in the table are minimum and maximum upsilon dsk taken from Table 4 and Table 5 of reference, 19, for comparison. The fitted spiral galaxy disk mass to light ratios are upsilon dsk less than 1.0 except for NGC 2841 which fitted with upsilon dsk less than 2.0. A good reference for fits. To spark data can also be found in reference 20, especially for spiral galaxy NGC 2841, where from our table 2 we have an average of upsilon dsk equals 0.856 m/l and bull equals 1.254 m/l each, of which is of the same order of magnitude as the fitted values. Disk equals 0.81 plus or minus 0.05 m/l and bull equals 0.93 plus or minus 0.05 m/l, respectively, from Figure 1 of reference, 20. For each plot of the galaxy rotation velocity, the Newtonian velocity curve is also displayed. Plots for the results of the spark galaxies can be found in Figures 2 and 3. Galaxy MB BTFR Ver MAE M10 plus 10, M10 plus 10, KMS-1, KMS-1. NGC 24031.6121.612.421.528.0.424. NGC 284137.27737.35667.671.476.0.189. DDO 154 0.0647440.02143.625.0.225.0.578. NGC 2915 0.2810 0.27998.064 0.814 0.653. Table 1. Results of fits to spark galaxy data using the graviton model. Equation 82, with masses from equation 80 and equation 81. The VAR are the mean error of the reported stellar velocities. The MAE errors are the average absolute error for the fits. Using final velocity as flat velocity. Rotation curve does not flatten. Galaxy average upsilon dsk average bull min upsilon dsk max upsilon dsk NGC 24030.5790.1.31.8 NGC 2841 1.0390.833 2.05.1 DDO 154 6.1830 1.11.2 NGC 2915 1.8740 Nana. Table 2. Results of fits to spark galaxy data using the graviton model equation 82. The columns for upsilon dsk and bull are the averages for the disk and bulge mass to light ratios determined by modeling the rotation velocity curve. 0 in the bull column means the bulge velocity is 0 in the data. Min and max upsilon dsk values for high surface mass galaxies from reference 19. Na means the result is not available. NGC 2403. NGC 2841. Figure 2, NGC 2403 and NGC 2841. Fits with spark data, the masses derived from equation 80 and equation 81, with velocity profiles for gas, disk and bulge. For mass to light curves, upsilon dsk is the solid line in filled circles, bull is the solid line in open squares. For rotation velocity curves, the solid line is the minimized fit to the data with the graviton model equation 82, and the dashed line is the Newtonian velocity. Top half, upper, mass density. Middle, mass to light ratio. Lower, the model velocity versus radial distance from the galactic center and the Newtonian velocity. Bottom half, upper, mass density. Middle, mass to light ratio. Lower, the model velocity versus radial distance from the galactic center and the Newtonian velocity. Spark galaxies DDO 154 and NGC 2915. Two dwarf galaxies that have been difficult to understand in terms of missing mass are DDO 154 and NGC 2915. Figure 3 shows the results for the fits using the graviton model. The upper curve shows the mass density, the middle curve displays the m/l ratios and the lower plot shows the observed and predicted rotation velocities. With the graviton model for DDO 154 we obtained a total baryonic mass of Bary equals 6.47 times 10 plus 8 m, which is less than 2 times the detected luminous mass reference, 21. Of m asterisk operator plus mhi plus he equals 3.65 times 10 plus 8 m. Significantly, it is only 1/5 of the estimated dark plus luminous matter of dark plus lum equals 3.1 times 10 plus 9 m. Our fitted disk mass-to-light ratios have an average of upsilon-dsk equals 6.183 m/L, which is 3 times the published value of upsilon-dsk is almost equal to 2 m/L. For NGC 2915 we obtained a total baryonic mass of Bary equals 2.81 times 10 plus 9 m, where the stellar mass and luminous Hi. Mass reference, 22, reference, 23, MHI plus M asterisk operator equals 1.06 times 10 plus 9 m. This compares with the total dynamical mass MT equals 21 times 10 plus 9 m, which is 7 times the total baryonic mass derived by the graviton model. DDO 154. NGC 2915. Figure 3, DDO 154 and NGC 2915. Fits with spark data, the masses derived from equation 80 and equation 81, with velocity profiles for gas, disk and bulge. For mass-to-light curves, upsilon-dsk is the solid line and filled circles. For rotation velocity curves, the solid line is the minimized fit to the data with the graviton model equation 82. And the dashed line is the Newtonian velocity. Top half, upper, mass density. Middle, mass-to-light ratio. Lower, the model velocity versus radial distance from the galactic center and the Newtonian velocity. Bottom half, upper, mass density. Middle, mass-to-light ratio. Lower, the model velocity versus radial distance from the galactic center and the Newtonian velocity. Discussion. Regarding the baryon acoustic oscillations, BAO, in the primordial plasma and the resulting cosmic microwave background radiation, CMB, if the energy loss in the gravitational field due to the gravitational redshift of graviton energy is the cause of the apparent dark matter in the universe, implying that dark matter particles do not exist, then in density perturbations of the plasma just before recombination, the baryons, photons, and gravitons are synchronized and there is not a central region of dark matter particles as theorized in the Standard Model reference, 24, so that when recombination begins the photons dissociate from the electrons and the resultant hydrogen atoms begin to attract and form dense regions in the perturbation. Just how the graviton redshift energy loss affects the density formations in the plasma and how this affects the determination of the Hubble constant from the BAO and CMB modeling reference, 25, is an area which needs to be studied. Regarding galaxy dynamics, with the modified Newtonian dynamics, MOND, reference, 26, and reference, 27, there may be a way to compare it with the graviton gravitational redshift theory. MOND takes effect in galaxies at a distance where the central acceleration is around 1.2 times 10⁻10 ms-2 by affecting a transition in the gravitational attractive force from AR-2 to AR-1 form. On the other hand, the graviton gravitational redshift theory augments the Newtonian rotational velocity beginning from the galactic center, which allows to distinguish it from MOND. Referring to Figure 2, at a radius of r equals 24.59 kpc, the spiral galaxy NGC 2841 has an observed velocity of v equals 298.0 km s-1, and we calculate the Newtonian velocity of Vn equals 191.5 km s-1 using the spark data. The radial acceleration at this distance is ACC equals v2/r equals 1.171 times 10⁻10 ms-2, which is at the beginning of the MOND regime and, assuming we have the correct baryon mass within that radius, MOND would predict an orbital velocity smoothly connected to the Newtonian value Vn, but we see that it would be smaller than v by 106.5 km s-1. Another interesting alternative approach to modified Newtonian dynamics is given in reference, 28, which, by way of an additive inverse Yukawa-like term to Newtonian gravitation, purports to account for gravitational dynamics from solar systems to galaxies and galaxy clusters and to the large-scale universe expansion. There is an analogy between Ref. 29, EQ. 19, and our equation, 54, which can to be further explored. Conclusion. The graviton self-interaction model describes the effect of gravitons in free fall in the gravitational field, losing energy by way of gravitational redshift and cosmological redshift without emitting any radiation. General relativity was applied for both the universe expansion and for spiral galaxy rotation curves. By assuming a coupling coefficient kdm for the graviton redshift in free fall, the graviton model can account for the apparent dark matter in the universe being related to the baryon density. Likewise, the dark energy depends on the coupling constant d and the baryon density. Thus, the apparent dark matter and dark energy are replaced by two constants and the hypothesized redshift of graviton energy. In the case of the rotational characteristics of spiral galaxies, the graviton theory well explains the greater than expected galaxy rotational velocities in the spark data with only the baryonic mass derived from the gas, disk and bulge velocity data with fitted upsilon* operator ratios, with a galaxy-dependent coupling coefficient kg and with the total baryon mass conforming to the BTFR. It is apparent that the fundamental aspect of graviton redshift points to the need to include this in the general relativity field equations. Conflict of interest. The author declares no conflict of interest. References. Oliveira, F. J. 2022. The Theory of Gravitons in the Expansion of the Universe. JEPG, 8, 3. https://dx.doi.org/10.4236/jhepgc.2022.83041. 2. Oliveira, F. J. 2022. Theory of Gravitons in Spiral and Dwarf Galaxy Rotation Curves. JEPG, 8, 3. https://dx.doi.org/10.4236/jhepgc.2022.83055. 3. Dewar, A. 2009. Implications of graviton-graviton interaction to dark matter. https://arcs4.org/pdf/astro-ph/0901.4005. 4. Wikipedia, Lambda CDM model. https://en.wikipedia.org/wiki/lambda-cdm model. 5. Hubble, E. 1929. A relation between distance and radial velocity among extragalactic nebulae. Proceedings of the National Academy of Sciences, 15, 3, 168-173 https://dx.doi.org/10.1073/pnas.15.3.168. 6. Friedman, A. 1922. Über die Kr among the ROMs. Zeitschrift für Physik, 10, 377-386. https://dx.doi.org/10.1007/bf01332580. 7. Lemaitre, G. 1931. Expansion of the Universe. A homogeneous universe of constant mass and increasing radius accounting for the radial velocity of extragalactic nebulae. MRAS 91, 5, 483-490 https://doi.org/1093/mnrs/91.5.483. Translated from Lemaitre, Georges, 1927. Un Univers homogène de masse constante et de rayon croissant rendant compte de la vitesse radiale de nébuleuses extragalactiques. Annales de la Société et Scientifique de Bruxelles, A47, 49-56. 8. Robertson, H. P. 1935. Kinematics and World Structure. Astrophysics. J. 82, 284 to 301. https://dx.doi.org/10.1086/1436881. 9. Walker, A. G. 1937, on Milne's Theory of World Structure. Proceedings of the London Mathematical Society, Series 2, 42, 190-127, https://dx.doi.org/10.1112/palms/s2-42.1.90. 10. Einstein, A. 1918, über Gravitationswellen. Sitzungsbericht der Königlich-Preußischen Akademie der Wissenschaften, Berlin, Seat 154-167. https://ui.adsabs.harvard.edu/abs/1918spaw.154e/abstract. 11. Einstein, A. 1952, The Foundation of the General Theory of Relativity. Dover Publications Incorporated, New York. 12. Suzuki, N., Rubin, D., Lidman, C., Aldering, G., Amanullah, R., Barbary, K., et al., 2011, The Hubble Space Telescope Cluster Supernova Survey. V. Improving the dark energy constraints above Z greater than 1 and building an early type-hosted supernova sample. Astrophysics. J. 746, 1, 2201168. https://dx.doi.org/10.88/0004-63x/746/1/85. 13. The Cosmological Parameters, Chapter 21. Updated by O. Lahav and A. R. Little. https://pdg.lbl.gov/2011/reviews/rpp2011-rev cosmologicalparameters.pdf. 14. M. Tanabashi et al., 2018, Particle Data Group, Phys. Reverend D. 98, 030001. Fields, B. D., Molaro, P., and Sarkar, S. 23. Big Bang Nucleosynthesis, https://pdg.lbl.gov/2018/reviews/rpp2018-rev-bang-nucleosynthesis.pdf. 15. http://astroweb.cwru.edu/spark. 16. Lely, F., McGaw, S. S. and Scombert, J. M. 2016, Spark, Mass Models for 175-disk Galaxies with Spitzer Photometry and Accurate Rotation Curves. Astron, J. 152, 6, 157-170. https://dx.doi.org/10.3847/0004-6256/152/6/157. 17. McGaw, S. S. 2005, The Baryonic-Tully-Fisher Relation of Galaxies with Extended Rotation Curves and the Stellar Mass of Rotating Galaxies. Astrophysics. J. 632, 2, 859-871. https://dx.doi.org/10.1086/432968. 18. Lely, F., McGaw, S. S. and Scombert, J. M. 2016, The Small Scatter of the Baryonic-Tully-Fisher Relation. Astrophysics. J. Let. 816, 1, L14, L19. https://dx.doi.org/10.38477/2041-8205/816/1/L14. 19. De Block, W. J. G. and McGaw, S. S. 1997. The dark and visible matter content of low surface brightness disk galaxies. MRAS, 290, 3, 533-552. https://dx.doi.org/10.3/mnrs/290.3.533. 20. Lee, P., Lely, F., McGaw, S. S. and Scombert, J. M. 2018. Fitting the radial acceleration relation to individual spark galaxies. Astron and Astrophes. 615, A3. https://dx.doi.org/10.1051/0001-6361/2017325547. https://dx.doi.org/10.1051/0004-6361/2017325547. 21. Kerrigan, C., and Patton, C., 1998. The total mass of DDO-154. Astrophes. J. 506. 1, 125-134. https://dx.doi.org/10.1086/306227. 22. Muir, G. R., Kerrigan, C., Beaulieu, S. F. and Freeman, K. C. 1996, NGC 2915. 2. A dark spiral galaxy with a blue compact dwarf core. Astron, J. 111, 1551-1575. https://dx.doi.org/10.1086/117895. 23. Muir, G. R., Blakesley, J. P., Sinani, M., Ford, H. C., Illingworth, G. D., Benitez, N., et al., 2003. The discovery of globular clusters in the protosporal galaxy NGC 2915. Implications for hierarchical galaxy evolution. Astrophes. J. Let. 599, 2, L83, L86. https://dx.doi.org/10.1086/381317. 24. Beutler, F., Blake, C., Collis, M., Jones, D. H., Stavely Smith, L., Campbell, L., et al. The 6DF Galaxy Survey, Baryon Acoustic Oscillations and the Local Hubble Constant. Mon. Not. Royal Astron SOC 416, 4, 3017-3032. https://dx.doi.org/10.11/j.1365-2966.2011.1950.x. 25. Planck Collaboration, Aghanim, N., Akrami, Y., Ashdown, M., Almont, J., Baxigalupi, C., Ballardini, M., et al., 2020. Planck 2018 results. 6. Cosmological parameters. Astron, Astrophes. 641A6, 67 to 139 https://dx.doi.org/10.1051/0004-6361/2018333910. 26. Milgram, M. 1983. A modification of the Newtonian dynamics as a possible alternative to the hidden mass hypothesis. Astrophes. J. 270, 365 to 370. https://dx.doi.org/10.1086/1611130. 27. Milgram, M. 1983. A modification of the Newtonian dynamics, implications for galaxies. Astrophes. J. 270, 371 to 383. https://dx.doi.org/10.1086/1611131. 28. Falcon, N. 2013. Modification of the Newtonian dynamics in cosmology, an alternative approach to dark matter and dark energy. Journ. Mod. Phys. 4, 10 to 18. https://dx.doi.org/10.4236/jmp.2013.48a003. 29. Falcon, N. 2021. A large-scale heuristic modification of Newtonian gravity as an alternative approach to dark energy and dark matter. J. Astrophes. Astron, 42, 102. https://dx.doi.org/10.1007/s12036-021-09752-0.